So in this, I'm simply going to have a continuation from our previous classes working. With this one, it's a combined situation or a mixed circuit that we have. So we want to take this information properly as we are having our question. Thus, we have a 525 50 hertz star connected alternator. So take note. We have got a star connected alternator, which is definitely not in three phase. And what does it do? It supplies this alternator here, supplies, meaning to say the 525 is going to be supplied, current is going to be supplied where? To a delta connected load. They are supplying to a delta connected. So our load is in delta. What is supplying the alternator? Star connected. All right. So take note there, guys. Take note on this part. So working with this question, I want us to take our information. And on our information, I want us to be careful. I'm just going to separate two things here. Our supply, which is our alternator, because we've got our supply as the alternator, which is what? Star connected. It is what? In star, this one. And we have the load. It is supplying what? The load. So our load is what? Is in delta. Take note, our load is in delta. So this is what we have. From the supply, we are given that the voltage there, which is the given values, remember they're line values. So we're given the line value of 525 volts. In what? In star. So what does it mean? It means we can have the phase value. Remember in star VP, we talked about this, guys, is VL over what? Square root of 3. So that's 525 over the square root of 3. So we must divide this by square root of 3 to obtain the phase value, which was going to be 303,109 volts. Take note, what we are having on our question, they are saying the alternate, this one, it supplies the load. So the line voltage here is the one that we are going to be seeing on the load. It is supplying. So we're going to see what? This on the load. So it is like this, guys. Remember, it is what? A star to all right. Just gonna have something like this. Maybe we can see. So it is just like this. To what? It's gonna go there to something which is what? In delta there. So if you are to consider the voltage will be the same, even the line value there, okay? The line current, it will be the same thing. We have a star and the load there in what? In delta. So we'll be having same in that the line values. So this is our consideration. So it means in our delta, we have the line value there, which is what? 525. But remember, in delta now, the phase value is equal to the line value. So it means, therefore, our phase value is going to be what? 525 again. There's no effect because in delta, they're the same. So you must be careful, guys. All right, no problem. So the information there was from the alternator supplying the load. But let's take note about this. All right, we're given there the frequency of what? Of 50 hertz, which is fine. The load which is being supplied, that one, the load, it has a resistance of per phase and inductive reactance per phase. That's we are dealing with a lagging perfect inductive. So take note. The load is the one that we are given its information, not from the what? Not from the outer, but on the load. The load is the one that has got this impedance, and this is impedance per phase because we are given what? Resistance and inductive reactance. So meaning to say we have impedance per phase on the load, not the alternator, but on the load. So this is going to be what? 4,75 plus, remember, inductive you add. So that's our JXL, which is what? 12 ohms per phase. So the question was, from this, determine the following. A, the potential difference across each phase of the load, because we'll be considering this as what? As in what? A balanced load. So in our calculations for N5, guys, we shall be working with what? A balanced load. The unbalanced actually for N6. So if you want to know more about the unbalanced load, make sure that you visit N6. They have notes, the videos that I did on the unbalanced load, you see. It's just one and the same. All right, so no problem. So this is what we have. Potential difference. But of what? We need to consider where it is to be considered. Where? Of the load, but is the potential difference across each phase, that is the phase voltage. So we already have this, guys, from the information that we just listed now from this that it is supplying. So meaning to say, therefore, in delta, this is what we are going to have on our load. The load, remember, is the one that is in delta. So meaning to say, this part, it's already answered, guys. Our voltage, we already have this one. Our VP is what? 525 volts. I explained how it happened there. All right. B, the current through each phase of what? Of the load. We are still on the load. And we want the current through each phase. That is IP. So that's B. The current through each phase. That means we are in what? Considering the part of what? Of the load, sorry. In this case, we are still working with the load. So remember, current, how do you determine your current from our previous calculations? We said current, simply the phase value for voltage over the impedance. So I say that we are going, if you're given information like this, you take your VP always as reference when you're just given like this. All right. So your VP will be in reference, meaning to say its angle is going to be what? At 0 degrees. As it is in reference, it will be at what? At 0 degrees. As for the impedance, it is the one that we are going to convert this one. Remember, this is in rectangular form. So from our calculator, we can convert what? To our polar form. So that's shift polar form here. So it's going to be 4,75. All right. Then we're going to have shift this one, close bracket, 12. All right. Then we close this bracket here. So it's going to give us our value in what? Polar form. So that's it, guys. 12,906. And our theta was going to be 68,405. This one. Okay. So that's it there. We have 12,906 and the angle being 68,405 degrees. So that is it there. As we have our impedance and our voltage there, we can determine what? Our current. So this one was direct, guys. We are dealing with the load. You have this side, not on the alternator, but here on the load. So therefore, the phase current was going to be calculated. Our VP is there, 525. I said on the reference, meaning to say it's at what? At 0 degrees. We calculated the impedance per phase. That's 12,906. And the angle, our angle is what? 68,405. So just like that, guys, we are back. Repetition, now and again, our polar form. So let's divide here. That was going to give us 40,679, and the angle 0 minus this, it was going to be negative 68,405. So that's it. We have got our current. That's what we're going to have. So remember your calculations, guys. So that's the B part. Remember, they said what? The current per phase. That's a phase value that we are calculating there. All right. Then C, the current supplied by each phase of the alternator. We need the phase value, but from where? Alternator. All right. Sorry, guys. Sorry for this. From here, from the alternator. From the alternator. So how can we determine this? Because on the alternator, guys, we do not have the impedance. The impedance here is of the load. This one, it's of the load. So on the alternator, how can we calculate the current? Because we are supposed to use VP over what? Over ZP. We do not have this. What can we do? Remember that it is the alternator which is supplying the load. So like we had on our voltage, the line voltage is the line voltage there also on our load. So if we know very well, guys, if we know this very well, it means, guys, as we calculated, all right, let me remove this. Gonna just remember our values, okay? Just gonna remember this. If we know this properly, it means that here, remember, we were dealing with what? The load here. From our load, this is what we have the current. So I'm gonna take this value of our current here. Let me write it because it's of the load. We calculated this side of the load. So on the load, we've got our impedance. Remember, that's 12,9. I erased this one. Now I need to just write it, no problem. So you understand me very soon. Then we also calculated the current. So I'm going to take the first value that we calculated in what? In a polar form. Remember, in polar form, we ended up with 40,679, and the angle was what? Negative 68,405 degrees. All right. This is the current that we calculated here. This one. We are talking about what? The load. The load. All right. No problem. So I want us to understand it here from this concept. If we bring back our information to this where we are. As we had previously here, the line voltage is the same. So as the alternator is supplying the load, what does it tell us, guys? It tells us the line current which appears here on our load was the same line current from the alternator because it is the one which is supplying this load. The line current. The line current. Just like the line voltage. The lines, the one that we consider, not the phase, the lines. So line to line. So if it is that the case, all right, I just hope we are going to win. So if it is our case here, we need the line value from where? From the calculation that we had here. Okay, sorry for that. Just gonna hope, guys, here. You're gonna win. Just didn't. All right, no problem. So at least our information is still there. So like I was saying, we just need the line values there. The line values. But in our case, we're gonna need the phase value later on. But what is it that we take here in delta to be brought here to our alternator is what is the line value. All right, so that was our consideration of the question, guys. Our question was to answer for the what? For the current which is supplied per watt by each phase of the alternator you're considering, our alternator. But like I said, from the load which is in delta, you're going to need what? We are going to need the line value. So from the load. All right. So from the load, we are going to need what? The line current. Remember, in delta. In delta, how do you calculate the line current? The line current in delta is equal to what? The square root of 3 times the phase value. So meaning to say, as we are having this phase value, we're going to take the magnitude there. So our magnitude is what? That's 40,679. All right, so that was gonna give us what? Our line current. So guys, use your calculator. I'm just gonna show you the value, which is 70, what? 458. That's why, guys, you see it's difficult for us to be showing you the calculator, this and that, because at the end, I think the screen will be having like a lot of information. So I don't know, guys, what happens with these softwares. They don't want like to have a lot of, or it's because I'm using these big softwares, maybe. That's why it happens like that. So this is it, guys. We took the line value, we bring it here. This is the same because it is connected. It is the one, the alternator is the one that is supplying. So what is supplying? Definitely supplying the same line value, this one. The same. So to the alternator there, we have the line current, which is what? 70,458 amps from the load. This is the one that is we have. But remember, they are saying we need the phase value for the alternator, which is connected to what? In a star connection. Remember, our alternator is in a star. So in a star, what is it that we know? The phase value is equal to what? To the line value in terms of our currents. So therefore, our phase value was going to be 70,458 amps, just like that. Just like that. So you see the connection of the question. Another information from Delta taken to this, another. So that is how questions can be like. So in our revisions, we just need to work out as many questions we do not know. How is it going to be in our exams, since this is the first part that we are having in our syllabus? All right. Anyways, let's move on to another part, which is D, the calculation of what? The power. All right. The power factor at which the load is operating. We are still here on the load. The power factor. Where can we calculate the power factor? I always talked about this, guys. The power factor from current, as our voltage is what? Is in phase. Remember, is in what? Is not in phase, but at reference. So as our VP was at 0 degrees, so it means the angle that you see on your current there is your phase angle. So our power factor was gonna be what? On our load. So remember, they said on the load. So we need the power factor on the what? On the load. Yeah, this side of the load. So that's gonna be cos of what? That's cos of the angle. So the angle there, that's 68,405. Do not worry about that negative, guys. Cos is not affected by that negative. Just calculate cos of the angle. That's 0,368. So that's our power factor. But if we consider our load in this case, as we are given that it is what? It has a resistance and an inductive reactance. It's an inductive load. So for inductive loads, it's going to be what? A lagging power factor. So in this case, we have what? A lagging power factor. We're dealing with what? Inductive load. Lagging power factor. You must be very, very careful in that presentation. So that is our lagging power factor. And we move on to the part of E, the power supplied by the alternator. So on the alternator, we remember we calculated the phase value there. We have got the phase value. Okay, we can use anything there. All right. On the alternator, guys, we've got anything because the phase value for for current is the same as the line one. So we can use any part here for the power. We can use power is equal to square root of 3 voltage, the line voltage times the line current times what? Our power factor. We can use this one because on the alternator, we can even use the phase values. All right. Remember your formulas for calculating for power, guys. We talked about this. So that is it. Voltage. Okay, everything is there from the alternator. So that was going to be square root of 3 times our VL, which is what here? Sorry, here is 525 times the current, our line current, which is from our calculations. Remember here, when you're saying in star, it's the same as in delta. So we got 70, 458. And the other thing this part here will be operating because the current was taken from the same current that we had. So it was operating at this angle. So it means it was gonna be working with the same phase angle. That's same power factor. So you'll be having same power factor of what? 0.368. All right. Remember, you calculated your power factor, 0.368. So that will be the condition. We took it from the same current. Remember when you took that one when you're calculating your current. So it's the same angle that you are working with. So that's the same power factor at the end. So calculating this, it was going to give us 23,577.516 in watts, which you can convert to kilowatts. Divide by 1,000. It's going to be 23,577. This is going to change to 8. That's in what? In kilowatts. If you want to have your answer in what? In kilowatts, you can have your answer because you're not told there. They just said calculate power. So it is up to you. Are you going to have your answer in kilowatts or in watts? It is up to you. So let's do revise, guys. More questions. We shall have more questions, more revisions to come as we are preparing for our exams, which are ahead of time.